Hello, today we're going to go over effusion and diffusion, which I think you probably didn't learn in honors, and we're going to talk about real gases and how they differ from ideal gases. All right, so first, what is diffusion and what is effusion? They're very similar sounding words, and they describe, in our case, the behavior of gases, but you've probably also heard at least diffusion in biology. So diffusion is movement from a high concentration to a low concentration. And with gases, it happens when we have something like a partition here. All right, and we have all our gas molecules over here, and there are no gas molecules over here. And if we remove the partition, then slowly, because our gas particles are constantly moving, then the particles end up dispersed throughout that entire space that they're given. All right, so how quickly they diffuse to be evenly distributed is going to depend on how fast they're moving, which is going to depend on the temperature, because that's how we determine our kinetic energy. And it's also going to depend on how large or small they are. So remember that particles at the same temperature have the same kinetic energy, but kinetic energy is equal to 1/2 the mass times the velocity squared. So the bigger the particles are, the slower they will move at a particular temperature, because those two things are inversely related. All right, and now effusion, which might be a newer concept for you. So basically with effusion, we are still moving from a high concentration to a place where there is a lower concentration, but it's now through a small hole or opening. Okay, so in this case, our hole here allows some gas particles to move through. Okay, and then over time, we get an even distribution of particles on the inside and the outside, or, before and after. Okay, we can also think about this in terms of something like a balloon. So balloons are imperfect materials, and they have small holes in them. So even though it doesn't seem like that, the gas particles, for the most part, stay within the balloon. If you've ever had a balloon over time, the volume goes down over time because the gas molecules are slowly escaping through teeny little holes in the balloon itself. Okay, so just like diffusion, for effusion, how fast that effusion happens is going to depend on the size of your particles. Okay, so the faster they're moving, the faster or more likely they are to hit this hole and escape out of their compartment. Okay, so smaller particles tend to move faster, just like I said, because of the 1/2 mv squared. Okay, and smaller particles are more likely to fit through the hole than bigger particles, depending on what size the hole is. So in general, smaller molecules or smaller atoms will effuse faster than bigger ones. Okay, so if you have a balloon with a 50-50 mixture of oxygen gas, which is O2, and helium, which is just helium atoms, and you let the balloon sit for several days, when you come back, will there be more oxygen or more helium left inside? Okay, so oxygen, especially given there's two of them, has a mass of about 32 grams per mole, whereas helium has a mass of 4 grams per mole. So that's definitely much smaller. Okay, so as you let it sit, the helium is going to effuse out of the balloon more quickly than the oxygen is. So if you come back and you're looking inside the balloon, there'll be more oxygen relative to the helium. Okay, and you've probably seen this if you've ever had a helium balloon. What you'll find is that over time, there's a mixture of helium and other gases in there. And over time, the helium escapes faster than the other gases. And so as you have your balloon for a little while, it no longer floats because the helium is going away faster than the other gases in the balloon. Okay, so now let's talk about real gases and how they behave differently than ideal gases. All right, so there are a couple of factors related to the gas that can change how ideally it behaves. Okay, so our red line here, the one on the bottom, shows an ideal gas. Okay, so you can see that when the temperature is low, when the pressure is low. When the pressure is low, the two lines overlap pretty well. Okay, so 200 atmospheres is really high pressure. Remember, atmospheric pressure is 1, so we're like way down here. So at atmospheric pressure, usually gases behave pretty ideally. Okay, and that is because as we squeeze them closer and closer and closer together, as our pressure gets higher, then they're going to get closer to each other. And remember that assumption we made in kinetic molecular theory was that the volume of the gas itself is very small compared to the volume between particles. So as we push them closer together or increase the pressure, that volume between them is going to get smaller and smaller, and therefore the volume of the gas particles themselves is going to get more and more relevant. Okay? Similarly, if we have a gas that has bigger molecules, then its volume will be bigger and we'll be less able to ignore it. So if we had another gas on this this graph here, like helium, for example, is much smaller than argon, so it would hug more closely to the ideal line than argon does. Okay, but at low pressures, where we usually are, both of them should behave pretty close to what we describe as ideal behavior. Okay, so the volume of a gas becomes more important or more of a factor when we are at very high pressure or when we have large gas molecules or gas atoms. Right? The other factor is the intermolecular forces. So if you remember, we also assumed that gases do not have any intermolecular forces. They don't interact with each other in a gas sample at all. All right, so that is going to become less and less true as we get to lower and lower temperature. And the reason is when two gas molecules or atoms collide with each other, all right, they should, we assume, have elastic collisions, meaning they bounce off each other with the same amount of energy as they collided with each other. Okay, but as the temperature gets lower and lower, they move more slowly, and so they, as their speed decreases or their velocity decreases, then the kinetic energy that they have is not always going to be enough to overcome the small attractions between the atoms or the molecules. Okay, so as our temperature gets lower, they slow down and the intermolecular forces become noticeable because they don't have very much kinetic energy. But if we're at high temperature, okay, then they're moving very fast. They have a lot of kinetic energy, and that overcomes any sort of attraction between particles. Okay. Also, if we have gas molecules that are bigger, then they're more likely to have stronger van der Waals attractions or London dispersion forces, right? Those ones that all the nonpolar molecules and atoms have. So xenon, being just a single atom, it can only have dispersion interactions. Okay, it would behave less ideally than helium, for example, because helium would have very weak London dispersion forces because it's so small, right? Similarly, if we had a gas that was capable of, if it was polar or capable of hydrogen bonding, there aren't really many of those because, you know, those forces are pretty strong and so they tend to make liquids. But if we had stronger intermolecular forces, then you would get less and less ideal behavior from those gases.